Hello students, good morning. So in this semester you will study Engineering Mathematics 1. Its code is MTL1025 and I shall teach this course to you. Okay, so as discussed in my previous lecture, this course has three main portions. One is differential calculus, other is integral calculus, and then matrices or linear algebra. Okay, so before starting the differential calculus, okay, let us first try to know what calculus is. It is the mathematical study of change. It has two main branches. One is differential calculus and the other is integral calculus. What is differential calculus? It is concerned with the study of rates at which quantities change. It mainly studies the derivative of a function and its derivatives. Next is integral calculus. So integral calculus is a reverse of differentiation. It deals with adding infinitely many infinitely small numbers. An integral is the space under a graph of an equation, or sometimes called as area under curve. Next is fundamental theorem of calculus. It links the concept of derivative of a function with the concept of integral. First part, also called first fundamental theorem of calculus, is that I'm sorry, an infinite integral of a function can be reversed by differentiation. And the second part is also called second fundamental theorem of calculus, is that the definite integral of a function can be computed by using any of its infinitely many antiderivatives. This part has key applications as it helps in computation of definite integrals. Okay. Now, before moving further, let us first try to recap the function, what a function is. Okay, you have studied it earlier, so let us recap. Let x and y be two non-empty sets. A function or mapping from a set x to set y is a rule which associates to each element x of set x a unique element small y of set y. Okay, so this is the definition of a function. X values are called pre-images and y values are called images. Each element of set X has one and only one image in set Y. Distinct elements of set X can have the same image in set Y. So now we can visualize here. Okay, so set X is this and this is set Y. So this is function from X to Y is a mapping. Okay, so each element of set X is associated to a unique element in set Y. Okay, so here we can see this arrow denotes these points. Okay, that is image set fx is called the range of f. So these are the images, and this set is known as range of f. Okay, so now this entire set Y is called codomain of f. This entire set, which may have some elements which are not associated to elements of X. So that entire set is known as codomain of F. Next is, okay, so in your previous classes you have studied functions of only one variable. Now in this class, that is BTech first semester, and in this course we are mainly concerned with functions of two variables. Okay, so if for every x and y an unique value fxy is associated, then f is said to be a function of two independent variables x and y, and is denoted by z is equal to fxy. Okay, so it is equation number 1. Geometrically in three-dimensional space xyz, okay, this equation 1 represents a surface. The values of xy for which the function is defined is known as are known as the domain of the function. Okay, now we will discuss the partial derivatives, okay, of functions of two variables. So let z is equal to fxy be a function of two independent variables x and y. If y is kept constant and x alone is allowed to vary, then z becomes the function of x only. It's quite evident. Okay, so if y is constant, so definitely z will be a function of x. The derivative of z with respect to x treating y constant is called partial derivative of z with respect to x, and is denoted by del del x of z or del del x of f or f subscript x. So these are the different annotations for representing partial derivatives with respect to x. Similarly, we can define partial derivative with respect to y. Okay, and in this way, this del del x of z can be defined like this: limit h tends to 0, f x plus h, there is change in x only and y is constant, okay, minus fxy divided by h, where h denotes a very small increment in the value of x. Okay, similarly this del del y of z can be defined like this, where h and k are very small numbers. Now the partial derivatives of higher order. Since this fx and fy are themselves functions of x and y, sorry, they can further be differentiated partially with respect to x as well as y. So if we differentiate del del x of z, again with respect to x, we get del square z upon del x square, and it is also denoted by fxx. Similar way, fyy is equal to del square z upon del y square is equal to del del y of z. The same way, fxy means del square z upon del x del y. It can also be obtained like, first we obtain del del y of z and then differentiate that with respect to x. And fyx is equal to del square z upon del y del x is equal to del del y of del del x of z. Okay, so this was the regarding the definitions of partial derivatives and second order derivatives. Similarly, we can have higher order derivatives, third and more orders. Okay, now we will try to understand with the help of an example that how these partial derivatives can be used to study the rate of changes or the changes in practical situations. Okay, so let us first try to do this. Let f is equal to pi r square h. Okay, that is the volume of the cylinder. Okay, we are considering the situation of a cylinder and we are considering its volume as a function of two variables r and h. So let us denote it by f, or f r h is equal to pi r square h, right? Now fr means del r of this f is what? If we do it, it will be pi and h are constant, okay, because we are doing only the change with respect to r, okay. So h will be considered constant. So del r of r square, which gives me 2r and pi 2 pi rh. So this is my partial derivative of f with respect to the radius r, right? So partial derivative of f with respect to r keeping h constant. As only radius changes by the very small or tenuous amount, the volume changes by 2 pi rh. So here we can understand, okay, the significance of partial derivative with respect to r. So if we give a very small increment or change to this radius, okay, what will be the change in the volume of this cylinder? So that can be obtained by only this derivative that we can study with the help of partial derivative with respect to r. Next, it is just like we add a skin with a circle circumference 2 pi r and a height of h. So we can see here. So this is just like if r was earlier this and it is increased to by some extent this r plus this distance. So this is just like a skin added to the cylinder. Okay. Similarly, this fh, that is partial derivative of function f or volume of the cylinder with respect to height or h. So this is, if we do it, r will be considered as constant, pi again constant. So its derivative is simply pi r square. Okay, as only the height changes, this very small increment in height h plus by tenuous amount, as only the height changes by very small amount, the volume changes by pi r square. So this will be the change in the volume. Okay, so it is like just like we add the thinnest disc on the top of the cylinder with the circles area of pi r square. So it's just like, okay, we can understand it just like that very smallest disk is added or put at the top. Okay, so that way we can interpret this partial derivatives, okay, and its use with the help of an example. Okay, so thank you very much.